This video quickly goes through the ideas of diffusion, effusion, kinetic energy of a gas related to temperature, as well as velocity of gas particles. Remember, the ideal gas law tells us that the kinetic energy of a gas is directly proportional to its temperature. This graph, often referred to as the Maxwell-Boltzmann distribution, just shows at a given temperature. Now, this is showing us different velocities, but they could also be different energies. We understand that at a given temperature, there's a variety, in this case, of velocities. Some that will be traveling a bit faster, some that will be traveling a bit slower. But we could say at 2,273 Kelvin, this is the average velocity. And at 1273, this is the average velocity. And at 273, this is the average velocity. So, the higher the temperature, the greater the average velocity. Understanding that there will be some that will be moving faster and some that will be moving slower. Students often get confused by the different size of peaks. The peaks are just showing us the relative number of particles that are at that velocity, the relative number at that velocity. All this is saying is that the greater the temperature, the greater the variety of different velocities. So you don't have so many particles traveling at this speed, and some a little faster, some a little slower. So the greater the temperature, the greater the number of options of different velocities. Well, how then do we represent an average velocity? Well, root mean square velocity, and I love Zumdahl's words, is a special kind of average. It's an averaging of a varying quantity. And in our packets, so this is what we looked at in class, I took several different definitions from several different locations for us. But again, it's a special kind of average. We're taking a root mean square because we're taking an average of a varying quantity. The root mean square, and so we use this special kind of cursive U instead of a cursive V, is the square root of 3RT over molar mass. Now, our temperature, of course, is going to be in Kelvin. What kind of R would we use? Well, we're familiar with R as the gas law constant from the ideal gas law. However, how would we use 0.08206 liter atmosphere per Kelvin mole and somehow get velocity, meter per second, out of that? So actually, this is not the version of R that we're going to use. R, here we're going to use 8.314 joule per Kelvin mole. Well, how does that get us meter per second? Well, remember, a joule is 1 kilogram meter squared per second squared. Oh, so really, R is 8.314 kilogram meter squared per second squared Kelvin mole. So when we multiply it by temperature, the Kelvin will cancel. Divided by molar mass, the kilogram and the mole will cancel. We'll have meter squared per second squared, take the square root of that, and meter per second. So did you notice, for molar mass, which I like to represent as capital MM, that should be in kilogram per mole to be able to yield the units that we need. So the speed is dictated by the temperature and then the molar mass of our compound. So again, remember, the ideal gas law told us that kinetic energy is directly related to the temperature. If we have two gases at the same temperature, they will have the same energy. That does not mean they have the same speed. The speed will be dictated a lot by the molecular weight. Here's an example calculating for neon. Neon would be 20.18 gram per mole, or 0.02018 kilogram per mole. Just being careful with your math, we get 607 meter per second. As you can see, I quickly converted to miles per hour, and to get 1358, whoo! Sure do travel fast. Sure do travel fast. Now, diffusion is the spontaneous mixing of two gases due to their rapid random motion. NIMSY defines diffusion as looking at it as, the rate of mixing. The rate of diffusion is the rate of mixing. Where effusion is the passage of a gas through a small opening in its container. I very much appreciate next the illustration of Graham's law of effusion. Graham's law of fusion tells us that the relative rates of effusion of two gases, as long as they are at the same temperature and pressure, are an inverse ratio of the square root of their molar masses. So see, we have rate of effusion of gas 1. Again, it's an inverse ratio to the square root of its molar mass. So if we have a rate of effusion of gas 1 per gas 2, it'll be the square root of the molar mass of gas 2 over gas 1. Be very, very, very careful of that. A very common demonstration is one in which you take a glass tube and you immerse a cotton swab with hydrochloric acid and another cotton swab with ammonia. Hydrochloric acid, actually hydrogen monochloride, and nitrogen trihydride are really gases. And so they will readily leave, and where they come into contact, the HCl plus the NH3, remember ammonia plus an acid gives an ammonium chloride or an ammonium salt. So in this case, it would be NH4Cl, which is a white solid. And so you have these two pieces of cotton and this glass tube, and then you begin to notice the collection of this white solid. But if you see, the white solid collects and begins to form a lot closer to the HCl cotton ball than the NH3 cotton ball. Well, if we look at the ratio of their rates of, it would be diffusion, HCl, because it's such a larger molecule, it diffuses at a slower rate, or the rate of diffusion of NH3 compared to HCl is 1.5 times faster. So we're not going to meet in the middle. We're going to meet about 75% of the way toward the HCl from the NH3. We went over a couple of these problems in class. So here's one in which we're just finding the ratio of the rates. And so if you want to pause and take a closer look at that one. And then to just walk us through these next two. Example 2, the rate of effusion of a particular gas, not sure what it is, was measured and found to be 24 milliliters per minute. Remember, a rate is a change in something per unit of time. And so we'd be looking at a change in the quantity or the volume per minute in this case. Under the same conditions, which we would assume to be pressure and temperature, the rate of effusion of methane is 47.8 milliliters per minute. What is the molar mass of the unknown gas? So, I just chose to put the 24, gas 1, milliliter per minute over the methane. So then I know I'm going to take the square root of the molar mass of methane, 12 plus 4, so 16.6 0.05 gram per mole divided by, and this is what we're trying to find, this molar mass of this unknown. What I would do is to square both sides, but I'm going to go ahead and find what this actual value is. Those units will cancel out, and so 24 divided by the 47.8, we get 0.502, and that would be squared, and that will be 16.05 gram per mole over this molar mass. And so then, if I go ahead and square, I get 0.252, and that will equal the 16.05 gram per mole over this molar mass I'm trying to find. So the molar mass of the gas will be the 16.05 gram per mole divided by the 0.252. And we will get 63.7 gram per mole, which is incredibly reasonable for a molar mass of a gas. And we would expect it to definitely be a greater molar mass because it is not effusing at as great a rate as the methane is. Okay, let's look at this final example. It took 4.5 minutes for 1 liter of helium to effuse through a porous barrier. So, my rate of effusion will be 1 liter per 4.5 minutes. How long will it take for 1 liter of chlorine to effuse? Alright, so this is what I'm looking for. Okay, so it doesn't matter which I choose to call my numerator, but why don't I go ahead and, because I have helium first. So the rate of effusion of helium, so 1 liter per 4.5 minutes, over chlorine, 1 liter, and here's what I'm trying to find, my time. Well, that'll equal the square root of the molar mass of chlorine, 70.90 gram per mole, over the square root of the molar mass of helium, which is, I'm not sure I'm totally good on this, 4.00. Alright, so what I'm going to choose to do, I'm just going to get this to be a value. So 1 divided by my 4.5, that's actually 0.22 liter per minute, and that is over my 1 liter per time that I'm trying to find for the chlorine. I'm going to go ahead and just divide this out and take the square root. So 70.9 divided by 4, square root, and I get 4.21. These units would cancel. Alright, so I'm going to bring this entire quantity up, multiply both sides by that. So what I'll get is 0.22 liter per minute, and then that'll be 4.21 times the 1 liter per unit of time. Why don't I go ahead and multiply through? So I'm going to get 0.22 liter per minute equals the 4.21 liter per unit of time. So if I try to solve for that, I'm going to get 4.21 liters divided by 0.22 liter per minute. So 4.21 divided by 0.22, and we will get 19 minutes. We would definitely expect, because it's a larger molecule, that definitely the chlorine would take longer to effuse than would the helium. There's a couple other examples of this in your text. Please take a look at that, and as always, forward any questions my way. Thank you.